Okay, a very warm welcome to everyone here today. So thank you very much for coming. I hope you're going to have a very interesting day. It's morning and afternoon. Very importantly, I think everyone probably knows the details already. The toilets are just over the other side. Health and safety, I think if there's a fire, I'm not quite sure what the rules are. Presumably not use the elevators. There's a lift. There's a stairs, is there? Down?
Yeah, there's stairs both
sides as well. A sort of general housekeeping. There will be lunch as well, which I believe is going to be served just outside at about 1:10, hopefully. Hope you all keep the schedule. And obviously there's coffee outside as well, and I think you're probably more or less going to help yourselves at any time. But there is a coffee break at 11. But anyway, the main subject of today's seminar, or today's session, is about computer vision and remote sensing. I think we all probably have this common understanding that there's a great variety of applications in remote sensing nowadays, and I just wrote down a few of these, many of which are going to be addressed today, about disaster and risk management, urban detection and management, land cover classification, a very common one, change detection, another very common one, and increasingly using a wider set of modalities. So of course LiDAR is used a lot, satellite data, radar, but also unmanned aerial vehicles. And I think all of those we're going to see mentioning of, and also aspects around fusion in particular, content extraction and so on and so forth. So looking forward to a very exciting program. We've got 3 keynote speakers today, so thank you very much to those for coming. We have this split between 3 sessions, so we've got 3 sessions, one before the coffee break, one after, and then one after lunch. I'll be chairing the first session today. My name is James Ferryman from the University of Reading, and Dr. Hong Wei from Reading will also be chairing the second session. I think the issues we're going to be thinking about today are, as it says, computer vision meets remote sensing. So what are the needs, what are the challenges in remote sensing? How much is computer vision actually used today? What are the strengths of existing methods? What are the challenges? What challenges remain? Are there any factors which are blocking progress? And I think for us, one of the main motivations for today is to bring everyone in this room together. Because like many disciplines, I don't think perhaps the computer vision people, researchers, are speaking enough to those involved in remote sensing. Obviously there's some overlap and some interdisciplinary work, but probably not as much as they should be. And we hope that today's discussion and talks and keynote speakers will enlighten us about existing applications and existing methods in computer vision, but also will help inform us about what challenges remain. Today is not just a be-all and end-all. Hopefully, after the end of the day, we can go away, we can make new friends, and we can carry on discussions around these topics. And hopefully, perhaps we can put together grant proposals or collaborative bids and other ideas and other projects going forward. Just to say, at the end of the day, although it's not strictly mentioned on the schedule, we plan to sort of have a bit of a summary, perhaps sort of like a panel meeting, a bit of a session with perhaps the 3 invited speakers, and we bring those to the front, and then we have a discussion and try to answer perhaps some of the questions at the top of the program. So those questions about the challenges and the key factors blocking progress and so on. We use those to motivate that discussion at the end of the day. Hopefully lots of these things will be discussed by then, but anything else we want to discuss, we can talk about it then. Okay, so without any delay, let's move on to the first keynote speaker. So this is Uwe Stilla from Technical University of Munich, and as you can see here, the presentation is going to be called Change Detection of Urban Objects Using Point Clouds. Over to you.
Thank you very much for this nice introduction. I would like to thank the organizers for this invitation, and it's an honor for me to speak here in London about change detection of urban objects. We also have here very interesting urban objects, and it's a challenge to find changes in this situation. So I want to start with the general issue of the automatic change detection. It is of general interest, especially for monitoring dynamic processes which show a confusion situation for human observers. If you have very complex structure like a city and you have 2 images from the city, and then you have to find what are the changes. It's easier if you have a highway that is not confusing, but you have this very detailed structure that's confusing. And independent on the sensors, means photogrammetry, laser scanning, or a radar, the 3D geometry of urban objects is often represented by point clouds. So I take the term point clouds, independent on in which way we receive the point clouds, and I will show you finally two different examples. The challenges are to detect small changes in extended urban areas showing complex structures. So the first example is going on a comparison between 2 point clouds, which were taken at different time. And the change detection is also interesting if you have a special object of interest in a rapidly changing environment, and this is especially on construction sites. So the second example is on progress monitoring, comparison of point clouds and a building information model BIM. So let us first start with the comparison of point to point cloud. And we start with a device for taking point clouds here with airborne laser scanning. We have an aircraft, helicopter, in this case we have then, we have a laser scanner. This is a full waveform scanner with a polygon mirror and scan lines, and additionally we need information about our position by GPS and our orientation IMU in all 3 angles, and also the time is important in this case. The very special thing here, which is not very common in remote sensing photogrammetry, is that the laser scanner is not looking downwards in a nadir view, it's looking in a forward-looking way, which is typically for military application, for example, obstacle warning systems. What you can now see here is a scan, and what we see are our technical university, and that is about the velocity where we are flying over the terrain, and here color-coded different height. You can also see, for example, this is my office here. This is the window. It's my office. Very interesting here on this laser scan is that you have in the oblique view, you are able to see the facades and the roofs. Facades and roof. But the drawback is that you have shadows due to the oblique view. And now the question comes up, how can we fill this 3D point cloud? And this can be filled by multiple views, by multiple flights. We had here a cross flight from different direction, and if you have multiple observation, in this case we have 4, then the problem comes up that they fit not exactly together. And co-registration is very important for change detection. Otherwise, each change is by a point which is not at the correct position. You can see here the 4 flights with 4 different colors. That is the clock tower here on the left, and you can see a profile here. Here's my office. The profile here from the building that fits not exactly together. So we are looking for methods doing an automatic co-registration from these displacements which come from inaccurate relative sensor position, means from the sensor, IMU, GPS, and the laser scanner, and or errors in the navigation data. So for doing this co-registration, we need some tie points or tie phases, and for that first we have to classify the scene. So what we are doing first is we are trying to find the ground level by reaching growing algorithm, here in blue. Next we are trying to find the facades, the roof structures. We try to fit planes into the roof structures by a Ransack algorithm, and then when we are not able to fit the planes into the point cloud, then we know that's vegetation. So we have 4 classes, and these 4 classes are just for finding where are the roofs, the roof faces. You can see this for the 4 different views. You see that these are 4 different views because the shadow situation is different from the 4 flights. Now we are taking the roofs, and if you have 2 roof planes and intersect them in space, then you have a line. If you have a 3rd roof place, then you have a virtual intersection point in space, and you can use this virtual intersection point as a tie point to combine with the other point clouds. That is the item. That is done automatically, fully automatically. So finally, this is now, you can see here, the scan. The first scan comes from south to north. The next scan with the co-registered point cloud from north to south. Here the facade is missing. Here also some structures can be seen because a little bit side looking. Now here the facades are coming from west, and the fourth comes from east in this direction. Now you can see in the next scan we have a complete point cloud. You can also see the windows in the scene. So we are able to get such a point cloud, and you see different colors, points coming here from the different views. Here in yellow, and they all the other green and light blue, the different colors. You're also able to look below the bridges here, and that is completely different what we have in classical laser scanning. So now let us assume that we have a situation that we have created such a database at time step T1, a not time critical situation. We have multiple scans. We do an automatic calibration of the sensor system during the flight. It's possible to do it during the flight. We have offline data processing, and we do a coarse classification of the scene into vegetation, buildings, ground, and so on. We have very good GPS data. We can also build up a reference station. Now we have this database, and we are coming to the situation T2, probably after a disaster, or we have a special task, or what happens, flooding, I don't know, fire, and we have a helicopter UAV mission. We have a forward-looking sensor, which is typically used for obstacle avoidance. We have degraded GPS accuracy, probably no reference station close to that. We have a scan line method. We are processing the data during it is recorded, more or less along the scan line. And what we want to do then is the data alignment, and if we are able to combine the data of the second scan with the first data, we can also do an automatic navigation of the carrier, because we know that we can use this co-registration data for navigation. So in the final task now is a comparison change detection. Typically, when we have classical data approaches, for example, of digital surface models, they are typically interpolated, put on a 2D grid. Works best with nadir view because we have more or less no occlusions by the buildings. We can update maps and can compare point clouds, but all other information about the point clouds get lost. I explain it in the next image a little bit better. Our method is to take into account where was the sensor and where's the point we observe. You can see, for example, here from S1, where is our sensor, here's our laser point. There must be a way between the sensor and the point, which is free. So we know that it's free, there's nothing in between. So this is an empty space. The point which are found is occupied, and we know nothing what is behind the point. So we have three different classes, and we handle this by the empty and occupied spy, that we can also consider the occlusion and changes implicit in that way. And this works very well with multi-view data. We start with a so-called occupancy grid, which is well known from 2D robot mapping. There are different methods to use that. You can use it by a probably probabilistic approach. We have used the Schaffer theory to combine the information. And in contrast, what is done typically in robot mapping, 2D robot mapping, our approach, we are working in the 3D world. We have 3D grids, and this cell size is comparatively wide because we use the cells just for the search structure. Search structure, I will tell it in the next slides a little bit more detail. We formulate it in that way that in case that we found a point, we have a certain uncertainty for this point, which is given typically by the laser footprint size, by the energy distribution, by the point position and accuracy, and so on. We can say we expect here an event, an object, a point, and we can also say that the way before must be free, otherwise we haven't seen that point. So that we have here a confidence for the empty space, we have a confidence for the point itself, and we have a confidence what is unknown. All this other things is unknown. We can say nothing about that. So we are working with these three data sets, or these three states. In this theory, the Dempster rules of combination, we can combine different observations, for example, from two rays, without going in detail, in a very easy way. Because this theory delivers these combination and the fusion of these different spaces for the occupied space as well as for the empty and for the observations along the laser beam. So we are storing the indices where we have a set of indices where are laser points in these cells, and we are also store the indices of the laser beams that traverse these cells. Both are just used as search structure to find other points. So we have index fields, and we know, okay, this, in case that probably here is a point and another point, they're in the same cell, then we have to consider both points in this theory. The same is given when we have different rays along this voxel to find neighboring or intersecting rays more or less in space. The basic idea now behind is the following. When we have this search structure, we are formulating the change detection by conflicts. That means, in case we have seen a point by a sensor which is Q, and before this space was empty because there are, in the first observation, there are trays, then there is a conflict. When I see here a point in the first observation, T1, then in T2 I see here a point, there is a conflict, we call that conflict type 1. Conflict type 2 is the following. We have seen an occupied space, a volume, but now we are able to see a point which requires that the beam has traversed this occupied space. So there's a conflict. We call this conflict type 2. The combination of the different observation is used by the Dempster-Schiefer theory. I want to show that with an example. We have 6, 7, 8 spots in Germany. We use this. One of my favorites is Abenberg, a small village, which was taken in 2008. In April, we have the combination of 4 views. We have 4.5 million points, and we have here cell size of 2 meter by 2 meter for the search structure. 1 year later, but in August, we have a flight over this same terrain, and we are interested what has changed during this flight. And we have just 1.5 million points because we are on one flight over the terrain. So what we can find, most changes of type conflict 1. There is something new what was not in the first point cloud. This comes mainly to the seasonal changes, vegetation. All the trees, for example, type 1. But we have also type 2. You see it here. There is something which is not still present here, was present before. This processing, and I have not explained that in detail. This is 1, this is 2. Probably can show it here. Is done during the flight, online during the flight. You can see that here. Green means we see the same point. Conflict 2, conflict 1. That is the scene that can be seen during the flight directly, is programmed in that way. Let us have a closer look to the details. We have the confront planar area, we have the unchanged ground, and we have unchanged surfaces, conflict 1 and conflict 2. And you see, for example, now here some details. Here's a castle, and you see, my mouse is not able. You see, for example, here some cars on the castle. Here you see a building complex. Here a different field situation with crops. And here you see a situation which is taken 2008, 2009, 2008, 2009. I can switch. There are some changes, and that is the result. The result is these cars are missing. This flag is different. You see this yellow points. You see also this car, this area, this building are missing, but this car is new. And you see here, for example, here is a scaffold in front of this building. This was the first example about change detection. we are on a level that we said we are not interested in an object, we are just interested in the changes in the point cloud. Second example now comes from comparison of a point cloud to a model. That is a very foxy thing, I can say. We are interested in progress monitoring, but we are not interested in progress monitoring of the inhabitants. We are interested in the progress monitoring of the building of the cave. So the idea behind that is this progress track is a research project. The operating sequences of building project are extremely dynamic, and we have selected this issue to find methods and to develop methods for the changes. Especially we have the difficult predictable boundary conditions, the weather in the building project. We have strong dependencies on single process step, which is a little bit different to other manufacturing lines, for example, to automotive industry. In the construction side, you need first this structure, then you can build the next structure. The acquisition of the actual construction progress is essential for cost controlling and organization of the further working schedule, and up to now these construction sites are manually inspected by a site manager and documented by a handwritten construction diagram. What we are planning is an automatic acquisition. Now this can be seen in this life cycle of building information model, which starts with the programming, conceptual design, detailed design, simulation, documentation, fabrication. Here we have the construction and the logistic, and this is the part we are interested in of the building model. The 4D construction means with time, 5D with money, and the construction logistics. So we have on one hand a BIM, which gives us this as planned state with a schedule and the 3D geometry and object attributes. At a certain state, TI. At the same time, we are able, TI, to monitor this construction site by photogrammetry, data acquisition, image orientation, dense matching, co-registration, so that we have a 3D point cloud. Then we have to compare the 3D point cloud with a model. In case that the comparison gives the result okay, then we go on to the next step. In case that is not showing not the same situation, we have probably to change the schedule of the building construction process. I will show that on one example here in what we have done in Munich. This is a building very close to the main station, just 5-minute walks between the university and the main station. Looks not very nice. You see here a different view. So I don't know who has decided that to build here a new building. And the architect's plan, here we need such a nice building. So they have planned this building, and after some months they started with the construction. Means the old building is away, and they started with this ground level work. Well, typically they are working in the construction on the construction site with 2D maps. So everything is on 2D maps. You see all the levels here of the building for the construction, but the planning is done in 3D. So the question comes up, why not using this planning information, the 3D model, also for monitoring, and especially in case that you have this, for the design, you have this temporal aspect, you can build a 4D model. And that's typical, this temporal aspect is given because there is a construction plan. This is in German. For example, here in this 3 days they need for the walls and for the parking devices, and should be done between the 2nd of May and the 6th of May. So each part of this building model has a timestamp when it is planned to be built. So when you introduce this information into the model, then you can create a model, and you can shift here the time in the model and can say, okay, how looks that probably in September or in October? Yeah? So each part has a time when it started to build up and when it's finished. Now we are coming to the computer vision, to the photochromatic side. We want to do an acquisition of the actual state with cameras. An example to do that is to mount a camera. That was our first idea on the crane here at this position. And what you then receive, taking photos every hour. This starts in April and ends in October, this video. But you can have every hour one picture, and you can see the progress, especially for ground truth use. But what we don't have is the stereo information. We want to create point clouds. So what we need different camera positions. That is the problem. If you come with a laser scanner on a construction site, they say, stop, first we have to finish that, then you can do it. So when you are working on a construction site, they accept not that you have now to take photos or to scan. What you have to do, you have to queue into the line. When it's time for you, then you can do the images. So our idea was first to do the terrestrial images of the construction site, and from beside these terrestrial images, we have also taken images from the crane here at the different position, and you can also see here, for example, here are images taken from different views, which were here at the buildings, for example. So you see the yellow circle shows the yellow image, the red position shows the red image, and the blue position here shows this blue image, so that we have from 3 different sides these acquisition. We have also terrestrial images taken here, for example, from the ground during the construction process, and then photogrammetry starts first in finding tie points between the images, and we also need this ground control points here, the red ones, which were measured, and especially those on the construction site, which were used, which are fixed over the entire process. Yeah, that's a standard approach is now to do an automatic selection of stereo pairs. From this stereo pairs, we typically calculate the depth value of each pixel by dense stereo. So we have depth maps, and this has to be fused together with the ground control points. And finally, you receive a point cloud taken by photos. This is a point cloud showing the situation in the beginning. A fused point cloud from different depth maps and different images. And you can also have the same for different time steps. I can show it a little bit construction situation a little bit later. You see also that you have here some holes. Not everything can be seen by the cameras here. And so on and so on and so on. So next step comes after this. And so on. Okay, so I stopped this video here. Now the question comes up, what are the changes? So you have the situation of the building model at a certain state and the point cloud from the photogrammetry. Now to find the changes. What are the changes in between? So we have the situation to find, for example, for the 15th of May, the situation, or for the 27th of June, or the 25th of September, and so on. And this is done. I will show that here in a simple example, here from this ground view. We have, this is what we get from the point cloud. And when I go now to, this is a model, point cloud model. And what we are trying now is to confirm which parts are still built and which not. So what we are doing, we have a rasterization of the object planes by a 10 centimeter tiles, and we try to find for each tile, is it already built or not, with a point density of about 2 centimeter and a sigma of about 1 centimeter precision of the points. Without going in detail, there are some confidences for the building parts. How confident is it that a certain object is built? And finally, we can accept that or not. All the results are coming back to the building information model. And what you can see here, now with the time slider, you see in gray as planned, in yellow as planned process. Green detected in time, blue detected ahead of time. So blue was ahead, green was in time, so they are a little bit faster here at this stage. Here they are faster with these objects, but here at the end there was probably due to the weather situation, they are exactly in time with the building at the end. Everything is covered. One problem which is addressed here are scaffolds in front of this building, so we have made some research to automatically extract the scaffolds from the point cloud and put it away from the other points. There are also some other ways to handle the problem, because the problem here is that we have more or less terrestrial views and not at all positions we are able to have a building around where we can take photos. So the idea comes up to use acquisition from air. And acquisition from air, we need high resolution. We thought about to use such a UAV. So probably you can start it here. It's difficult a little bit about the crane. If you have cranes, and we have a UAV, that you have no collision with the cranes during the acquisition here. On the construction side, it's a different construction site, which is in the south of Munich. Kindergarten, which is built here. And the best time is when they don't move the cranes. So on Sunday. Okay. I can stop this video landing. You see the UAV is working here. Takes about 5 to 10 minutes, then we have all images which we need. What we can see now is stop that. Now the mouse. Okay. So right click that here. Going back. This is what we see from the UAV in that way, and you see also here the construction situation at a certain time. Here a different situation also taken from the UAV, and what we finally receive from these different images is again a point cloud showing this construction situation at a certain stage. Here you see a different situation which is created from the images of the UAV. The next idea comes up, okay, in some cases it's difficult to operate with a UAV, probably in the inner city areas. We have not permission to use a UAV over the construction site. Why not mounting a stereo camera system on the crane? And one idea is to put that on the crane stand. The stereo system was our first idea. Or what we also can do, instead of putting that on the crane stand, we can put it on the crane jib, because the crane jib is moving over this area. So this was our idea, and we decided to mount it on the crane jib. Here you see the stereo camera system. The first camera is here, the second camera is here, and this is a situation where you can see the cameras on the crane, and here the crane jib is put it by mobile car crane to the main crane here. Here on the left are the cameras. So what you see from the camera is something like this from one camera. So you see only a part of the construction site, but due to the fact that the crane is moving, here you have different acquisitions, and you see more or less. This is a point cloud that was reconstructed from the acquisition. You can have a stereo between these two fixed stereo cameras, but you can also do stereo between these cameras. So we have multiple ways to do the reconstruction and intersection of rays, which you can see here, for example, in this situation, the cameras. And again, you are able to reconstruct here a point cloud from, this is the third construction site that we have. The third construction site, which is the hospital of our university, new building, part of this hospital, which is here, can be seen with this color of concrete, track of concrete in 3D. Okay, again the question comes up in this construction site. We have considered the visibility of objects in the same way we have done it in the beginning. Means we have to know which object parts we are able to see, what has changed, and what definitely we have no information about that. So a similar approach now is done or programmed, where we have these octree voxels describing the entire building, so that we can create a visibility map to say, okay, this part of the building was seen, so all rays from this camera to this part shows free space. We know there is nothing, definitely. Here, we see nothing. That means we have no information about that. We have always 3 states, and these 3 states are important for handling the problem. Yeah, this shows, for example, here in green, which is free, and blue, which is occupied, and in white, this is unknown. Yeah, photogrammetry and remote sensing are not magic. In general, we have used 3 different ways, and we are investigating the ways with the terrestrial handheld situation, the mobile airborne with UAV, and the mobile static views from a crane camera to explore that. I think I have some minutes to say something about
5 minutes.
Okay, so I will use it. You have heard about now from point clouds, from camera, and from mobilizer scanning, but I have talked in the beginning a little bit about some of you about radar. So I want to just show you 2-3 slides about radar. In radar we have the problem that the side-looking geometry is a must, and we have typically the situation that we have shadow areas on one hand, on the other hand we have this layover situation where we have a signal mixture. And especially in urban areas it's very, very difficult to reconstruct the point cloud from this aircraft. What we have done is the following. We have used a multi-antenna system with 4 antennas, which has 28 centimeters here on aircraft, and we have different flight paths, means multi-aspect. We are able to look from different views so that we can fill up the shadow areas on one hand. We have redundant data, which allows us to decompose from the mixed signals, the individual scatterers, by a more or less tomographic approach. Without going in detail, what we are doing by a so-called backward geocoding is that we have hypothesis for a certain scatterer. We are looking in the first stack where is the position of the scatterer, in case that we have here a certain position, a second position from the second aspect, and the third and the fourth aspect could be estimated. We are calculating the covariance matrix and doing estimation. We do a phase simulation to a probability density function, and we do that for each observation in this stack, and we select the best situation, the most probable situation for a height, which leads to a 2D height map looking like this. Same situation. Here's my office from the TUM area, and this can be overlaid with the structure. Here color-coded the height for the points from the radar acquisition. We have about 15-20 centimeter by 30 centimeter resolution about. And the point cloud is much more denser from compared to the LiDAR situation. Probably last image which shows the situation. You see here, this is an optical image of a building. Here you see the very smooth color-coded height values from the laser scan, and this is what we receive from the radar. Cannot compete with LiDAR concerning the accuracy at the moment, but it's one of the first attempts to decompose this problem of the layover and the shadow issue in urban area. This is the difference maps. At the moment we take the laser scan as ground truth for the radar. I hope I have not exhausted so much here. Thank you very much.
Thank you. Very interesting talk. Are there any questions? Please, at the back.
How did you find the noise difference between the LiDAR and the optical imagery for change detection? Did you find a lot more in the optical imagery?
I think in the optical imagery we have a much higher, or we have a much higher precision. So we're talking in the centimeter domain for the terrestrial acquisition, while in LiDAR we are in the decimeter when we have the aircraft. Typically we have problems. We also thought about, for example, for this progress monitoring of the building, to use a laser scanner, but it's difficult if you have a laser scanner on a crane. The crane is always it's not stable, and you need a stable situation for a laser scanner. Also, it's difficult to bring a laser scanner while people are working here and say, stop, I have here my laser scanner. In general, it's easier to handle a point cloud from the laser scanner than from the optical imagery, because you have all to do this dense matching. You have at least 2, 3, 4 observations to have a point which has a high accuracy. It's difficult to compare because they are terrestrial and airborne acquisitions.
Thank you.
I just have a question about your construction site example. So when you were registering your model against the point cloud data to determine the stages of the construction, what criteria did you use there? Because I could understand there'd be quite a lot of noise, and I think you hinted that there were some challenges around the matching process to determine whether there is something physically there or there isn't, or whether it's noise. What kind of criteria did you use for matching the model to the...
First of all, what we are doing is probably have here a hidden slide showing the situation. Going back to the construction.
Sort of halfway through, I think.
Yeah. So here.
Yeah. That's even earlier. Yeah.
Oh no, I have deleted the slides. It's not a presentation. Doesn't matter. What we are doing is an error propagation. So we know how precise measurement is when we have 2 rays. At least we need 2 rays for 1 point to have it. And so with this error propagation, you have different acquisition situation. You can say, okay, here we need a higher tolerance than probably here, because this was taken from different views, and they have a better, if you have 2 rays and that way, then you have a larger error compared if you have 2 rays in that situation. Yeah. So we consider the errors from the observations, and this is average values. We can also have probably here 3, 4, 5 centimeters and use that for the matching process. Okay. And for example, one problem is here. You see, for example, here this is concrete, but this part here was not detected because on top of this part there is this wood. Because
it's a different material, so it makes a big difference.
Yeah, and this is about this distance, so this was not detected. So we can also say we don't know is there any concrete inner or not. But finally, in the here this is a problem. Was not detected. Bauteil nicht vorhanden. We have only confidence of 29%. So we are working with confidence values which considers the acquisition and the observation of the points.
Sure. Yeah. Okay. Interesting. Yeah. Okay. One more question? Yeah.
You talked about the use of the airborne laser scanner, the forward-looking laser scanner in non-time critical situations. Can you give a comment on the use of it in time-critical situations? Maybe comment on the spatial scale or the rapidity of generating those data? This
is exactly what I have shown in this situation. Time-critical situation has 2 issues. I'll go back. So, now we are coming now to the point cloud. And this is exactly the situation that we have when we are flying, when we have the first flight over the terrain here. So in this situation, we don't have, or we assume that we don't have this high GPS information. We have no reference station. What we are doing is the following. In the beginning, we have seen that the matching process for different views are done by these faces from the roofs. And they are matched. And this is exactly what we do here. During the flight, we are doing a matching of the roofs, because these roofs are constructed step by step. Means that if you have a part of the line, you combine this line with the next line with the next line, and if you have a face, then you take this face, and this face is matched with the sensor. So that means by this matching process, you get your own position, your orientation parameters. So that is done during the flight over the situation. What we are doing is only that we have in one video stream, we are not comparing the entire point cloud of 4 views with the old 4-view point cloud. What we are doing is in one stream of the scan, we want to compare and to match this view, what we actually see with what we have in the database. So I think if you see, for example, the small changes, shows that it must be very, very precise. And we are talking about, I have also a list about the quality. The quality, these are different scenes we have investigated. And you see here the quality in meter. In meter the quality. And this is before calibration in red. In green after calibration, and in blue after co-registration. For example, these scene, what we have seen Abendberg here, the box I have showed you, we are about in 10 centimeter precision in this interval after automatic co-registration. Before we have here a very strong calibration error, which is estimated and corrected by a matching process.
Okay, I think we should stop here in the interest of time, but thank you very much.
Thank you much.
Thank you. Any further questions we can discuss at the end of the day? Okay, so on to the next speaker. I think it's Jordi.